Hello everyone, my name is Yuqing Cai. Today I'm presenting this work completed with Dr. Guanlin Dang. The topic of my presentation is GPU accelerate implicit ODE direct integration based on the Seulex method and application of a combustion benchmarking suite. This report is divided into the above 6 parts, namely the background introduction and the introduction to the GPU accelerate software package, and the simulation verification, and the result about the acceleration. A benchmarking suite named Film Test. We will show the relationship between the ODE solvers and the benchmark suite in the following section. And last is a summary and a prospect. As we all know, combustion simulation is a crucial technology that drives the development of the aerospace industry, while the computation of the combustion system is a problem. Here we show an example. Example that the second-order temporal integration works for the chemical ODEs. It requires the analytical chemical Jacobian and the solving of the linear equation. So the computation workload increased exponentially with the number of species. So it is very necessary to accelerate the computation. We noticed that the GPU has gradually become the mainstream in the development of scientific computing. This is the 2022 top 500 list of supercomputers. And we can see that among the top 10, 7 of them has adopted GPU accelerator cards as the core processors. In the field of CFD, GPU acceleration has attracted widespread attention and applications. For example, in the right, in this article, the GPU accelerated CFD code can be 2 orders of magnitude faster than the CPU program using 128 nodes and 512 GPUs. Surpasses the simulation speed of the CPU program with over 130,000 CPU cores. So the GPU is very fast and potential. But it is pity that in the field of the combustion simulation, especially for the chemical ODEs, there are few tries for GPU accelerate. We often use the Cantor, OpenFOAM, even the ChemKin to solve the chemical ODEs. These packages do not fully support for GPU acceleration, so this drives us to develop our GPU accelerator package. We named it OpenCC, the Open Compute Chemistry. Now I will show the main of this package. In this package, we employed the implicit Seulex method, which is based on the Richardson extrapolation. This algorithm selects the adaptive extrapolation level based on some error control criteria. Then it can make an adaptive step size, which is benefit to large integration step and save the computation time. Studies have shown that the Seulex algorithm has higher computation accuracy and efficiency. This diagram shows the problem processing of the Seulex algorithm. Firstly, we input the mole concentration, pressure, and temperature, and the time step size, and calculate it for different chemical variables such as the reaction rate and the analytical Jacobian matrix. And then the stability analysis of the Jacobian analysis must be examined. After that, the Seulex determines the extrapolation level and the step size through error control. When the convergence is okay, the loop exists. But when the convergence is failed, the substep are adjusted and the higher order extrapolation method is selected until the accuracy requirement is met. Finally, the updated mole fraction, pressure, and temperature are output. In our package, in our software package, the main functional modules includes the mechanical files reading, thermophysical property calculation based on the ideal gas, and the calculation of chemical reaction rate, and the analytical calculation and the construction of the chemical reaction Jacobian matrix, which is one of the most computational consumer, and the ODE solver method, we use the Seulex. The main feature of the software package can be expressed by the four parts. The OpenCC supports stiff detailed chemical reaction process solving, so it is high precision. And we have provided C and Python API interfaces. So it is very easy to integrate this package into any CFD simulation, which shows high versatility. Since the minimal dependence during communication and installation, our package is compatible with various graphics cards from the NVIDIA, Seulex DCU, and AMD. This is very high portable. And the high performance will be shown as the following section of our results. Well, we have used the YAML file as the mechanical readings because the YAML file, as we can see, is very friendly for human. And the Cantera is also uses the YAML file, so our package is compatible with Cantera. When we calculate the chemical ODE, we often use some constraint conditions, such as the constant pressure or constant volume. So we add a thermophysical calculation, also based on ideal gas, to update the density, specific heat, compressibility concentrations, and enthalpies through the temperature, pressure, and mass fraction. Well, it should be noted that the temperature often cannot be get directly from the CFD simulation because we often use the internal energy or the enthalpy as a variable of the energy equation in CFD simulation. So we update the temperature through the enthalpy using Newton iteration because we first approved the calculation of pressure density solvers. And in the chemical connector system, we use our Venus serial to calculate the chemical reactor rate and the analytical Jacobian solution. OpenCC supports solving the elementary reaction, third body reaction, and the different types of decaying reaction, such as the Lindemann Torr, which is almost covers the reaction types. Well, the CPU and the GPU is very different in the computer architecture. So we have developed a load balance method and CPU control algorithms to leverage the GPU performance for our package. For the load balance method, each group thread independently calculates a point chemical reaction, leveraging GPU multi-threading to faster computation. And using a global memory, store the local time, step, and reaction advanced for each point. If the end time is reached, the thread has further calculation. When all threads is the block end, few blocks are launched. And for the CPU control algorithms, each GPU thread had a flag using reduction to check it all errors meet the requirement. And the select loop breaks only if all of the thread errors meet the requirements. Then we have developed revenging higher temperature data with shared memory and automatic operations to accelerate the calculation in low temperature region. Well, in this section, we will show some results of the OpenCC in simulation verification for the zero-dimensional hydrogen combustion, homogeneous combustion, and the different temperature and the equivalence ratio. The calculation results of OpenCC can match those of the OpenFOAM and Cantera. Well, for the more complex methane mechanism, we have used the GR 3.0, also varying temperature and equivalential. The OpenCC results are also closing to the testing solvers. Furthermore, we compared the important component OH in the reaction process because it is a radicular component with a faster reaction characteristic. And we can see that the OpenCC solution is also consistent with those calculated. This page showed a two-dimensional verification. The DLR test case is a standard jet combustion tutorial in OpenFOAM, and we also can see the calculation results of OpenCC and OpenCC and OpenFOAM is matched very well. And at the next stat time, the calculation results are also consistent. This page shows the three-dimensional reactive Taylor-Green vortex is a recently established standard test case in the DeepFlame platform. We use this tutorial to test the OpenCC performance with all GPU scenery. It means the PDE solution is solved by DeepFlame in GPU. As shown in the figure, the results of CPU and DeepFlame, CPU version DeepFlame and the GPU version DeepFlame and OpenCC is very much well. So above is the accuracy verification. This page compares the efficiency between the CPU and GPU. For the DLR cases, OpenCC can achieve 20-fold speed up under different grid size. If only considering the speed up of the ODE parts, it could accelerate by the 50 to 80 times. If the PDE also adopted GPU acceleration, just like in the TGV case, the entire process can be accelerated by more than 100 times compared to the OpenFOAM. In addition to the zero-dimensional and two-dimensional case, we employed this package to simulate a swirl burner with the LES and the PSR model, and the result is reasonable. And this result has been applied by other research in our group and make 92-fold speed up compared to the one GPU or A of the NVIDIA and NVIDIA card named the A800 and was the one CPU core. Well, we have to say that the OpenCC is also need to be improved. So, in order to accelerate the development and verification of the numerical software, we create a benchmarking suite named Flame Test. This repository integrated several reference data from the classical solver, such as the Cantera, ChemKing, and OpenFOAM. The control module will invoke the test solver, such as the zero-dimensional test problem in OpenCC. It simulates the combustion process based on preset initial combustion condition and compares the simulation results with the reference data in this repository, automatically generating the comparison images and testing reports. The repository structure of the Flame test includes a 4-folder, the 0, 1, 2, 3 dimensional folder. Currently, the 0-dimensional folder has been basically set up. The automatic generated test report enables us to quickly identify issues or bugs in the development of OpenCC. And this page displayed the part examples of Flame test in the testing report of zero-dimensional simulation. This is a screenshot of the testing in zero-dimensional report. It helps us develop the OpenCC quickly. However, we just complete the zero-dimensional modules. It is necessary to add to the 2- or 3-dimensional classical problem, such as the spray from engine combustion network, the ECN, and the Sandia flame into the benchmark suite in the future. Okay, in this work, we have some conclusions. We have developed a GPU solver library to stiff chemical kinetic system, and the correctness test has been completed in zero-dimensional combustion, 2-dimensional DLR, and 3-dimensional TGV examples with different mechanisms. On the cushion supercomputing platform, the entire simulation processing of OpenFOAM can be accelerated by 20 times, and the ODE solving process is 50 to 80 times faster compared to the solver embedded in OpenFOAM. And in a full GPU scenario, the speed up can reach the 160 36 times compared to the OpenFOAM CPU solving. We have to say there are still some issues in our package. Includes the Jacobian calculation optimization and the PLU matrix decomposition optimization. The accuracy is okay, but the efficiency we think it can be improved in the future. So we have a prospect for the works in the future to optimize the Jacobian calculation and PLU decomposition for 3-fold speed-up performance boost, and support solving the real gas state equation and more reaction types, just like such as the third types of the decay reaction, named the SRI reaction. And we will expand more tests for flame test, including 1, 2, 3 dimensional plate problems, and conduct the combustion DNS and establish a turbulent combustion database. At last, we will develop a GPU accelerated combustion simulation software, OpenCC, that can, we hope it can compete the Cantera in the future. And this is the ultimate objective of our works. Thank you for your attention.